We already know that for this galvanic cell, solid zinc is oxidized to zinc 2 plus ions. Oxidation occurs at the anode, so this electrode is our anode. And copper 2 plus ions are reduced to solid copper. Reduction occurs at the cathode, so this electrode must be our cathode. If we start with a 1 molar concentration of zinc sulfate, that means in solution our initial concentration of zinc 2 plus would be 1 molar. And we have a 1 molar concentration of copper sulfate, which means we're starting with a concentration of copper 2 plus of 1 molar. So we're under standard conditions. We have 1 molar for our concentrations. We're at 25 degrees C. We have solid pure electrodes, and we know that the standard cell potential, so the cell potential under standard conditions for this cell is positive 1.10 volts. So we have a spontaneous redox reaction which produces a current. So electrons flow in our wire and we get a voltage. We have a standard cell potential. In one of the videos in electrochemistry, we took our standard cell potential and from it we calculated delta G0. So we used this equation. We said delta G0 is equal to negative NF E0. So we plugged in our standard cell potential and we got delta G0. So delta G0 is the change in free energy under standard conditions, and we got negative 212 kilojoules. Let's look at the equation for the change in free energy from thermodynamics, and let's analyze our galvanic cell. So the change in free energy is equal to the standard change in free energy, delta G0, plus RT natural log of Q. So remember, this delta G is the instantaneous difference in free energy between your reactants and your products. Delta G0 is the change in free energy under standard conditions. R is the gas constant, T is temperature in Kelvin, and Q is your reaction quotient. So let's think about what the reaction quotient is for this reaction. So for this reaction, our spontaneous redox reaction, Q has the same form as the equilibrium constant, concentration of products over concentration of reactants, and you leave out pure solids. So that would be the concentration of zinc 2 plus, right? That's our product here. We're leaving out solid copper, over the concentration of copper 2 plus, and we're leaving out solid zinc, so over the concentration of copper 2 plus. At this instant in time, we plug in our concentrations, right? The concentration of zinc 2 plus is 1 molar, so we have 1.0. The concentration of copper 2 plus is also 1 molar, so we're under standard conditions here. So Q is equal to 1 at this instant, and we plug in Q is equal to 1 into our equation, and we see that the natural log of 1, right? Natural log of 1 is equal to 0. So this term goes to 0. And under standard conditions, the change in free energy, delta G, right? The change in free energy, delta G, is equal to the change in free energy under standard conditions, delta G0. And that's equal to negative 212 kilojoules. And if you wanted to write per mole of reaction, right, you could do that right here. And so this makes sense because we're under standard conditions, right? We're at 1 molar for our concentration, so the change in free energy is equal to delta G0. Notice that delta G is negative, so we know this is a spontaneous reaction, right? This is a spontaneous reaction under standard conditions. So current flows, we get a voltage. So let's go back up to here. All right, so we get a voltage. We get a voltage at this moment in time. So the reaction goes to the right to make more of our products, right? We're going to make more of our products here. What happens to Q as the reaction proceeds to the right? Well, we're increasing the concentration of our products. We're increasing the concentration of zinc 2 plus ions. At the same time, we're decreasing the concentration of copper 2 plus ions. So Q increases as the reaction proceeds to the right. So as we make more products, right, Q increases. So we get an increase in Q. what happens to delta G? What happens to the instantaneous difference in free energy between our reactants and our products? Let's go ahead and plug that in to our equation. So let's make up a number. Let's say that Q increases from, we started over here with 1. Let's say that Q increases to 10,000. So we're to pick a big number here. So Q goes up to 10,000. So we have far more products than we do reactants. What is delta G? Delta G is equal to, delta G 0 is the standard change in free energy. So under standard conditions, this is negative 212 kilojoules. So that's negative 212, and this would be negative 212,000 joules if we convert kilojoules to joules. Plus we have R, which is the gas constant. So let me go back up to here. R is the gas constant, which is 8.314 joules per mole times Kelvin. So you could make this joules per mole here, so your units balance out, moles per mole of reaction. And then we have the temperature. So the temperature of our reaction, let's remind ourselves of that. So we go back up to here. We're at 25 degrees C. So 25 degrees C is 298 Kelvin. So this is 298 Kelvin. So Kelvin would cancel out here. And this is times the natural log of Q. And now we've changed Q. We've said, okay, let's just pick a number that's pretty big. So Q is 10,000. So we plug in the natural log of 10,000. So we have obviously a huge number of products compared to reactants at this moment in time. So at this moment in time, what is delta G? What is the instantaneous change in free energy between our reactants and our products? So we need to do that calculation here. So let's find the natural log of 10,000. So we have that. We're going to multiply that by 298, and we're going to multiply that by 8.314. And we're going to add that number. We're going to add that number to negative 212,000. So we get that delta G is equal to negative 189.2, let's say, kilojoules. So I'll make that into kilojoules. So delta G is equal to negative 189.2 kilojoules per mole. So I'm not really too concerned about the exact number. I'm just trying to point out what happens as you change Q. Right? So as we increased Q, as we went from Q is equal to 1 to Q is equal to 10,000, so what happened to delta G? We went from negative 212 kilojoules to negative 189.2 kilojoules. So we're getting closer to 0. We're getting closer to equilibrium. But at this instant, right, right here, when Q is equal to 10,000, we still have a negative value. We still have a negative delta G, I should say. So the reaction is still spontaneous. The reaction is still spontaneous. We're still going to generate a current. We're still going to make more of our products. We're still going to have a voltage at this moment in time. What would be the voltage at this moment in time? What would be the instantaneous cell potential? So the instantaneous cell potential is E. We could find that using our equation that relates delta G and E. Delta G is equal to negative NFE. So if we plug in delta G into here, right, we know that N is the number of moles of electrons that are transferred, F is Faraday's constant, and then E is our instantaneous cell potential. To save time, I won't do the calculation here, but if you do that calculation, you will get that your instantaneous cell potential is equal to 0.98 volts, positive 0.98 volts. So the reaction is spontaneous. We're still producing a voltage. We're still producing a voltage here. So notice that our voltage has decreased a little bit, right? In the previous example, under standard conditions, at that moment in time, the voltage was 1.10 volts. So we've lost a little bit of voltage here. We're down to 0.98. But think about how large that number is, right? We have so many of our products compared to our reactants, and we're still getting a pretty decent voltage. So approximately 1 volt, so pretty close to the original 1.1 volts. What happens at equilibrium? All right, so what happens at equilibrium? We know that at equilibrium, the reaction quotient Q is equal to the equilibrium constant K. And at 25 degrees C, K is equal to 1.58 times 10 to the 37th. So for this reaction at 25 degrees C, this is our equilibrium constant. Let's plug in our equilibrium constant into our equation for delta G to see what we get. So delta G is equal to delta G0, which was negative 212 kilojoules per mole, plus R, which is 8.314, times the temperature. We're still at 25 degrees C, so this is 298 K. And this time we're putting in the natural log of K. So we're plugging in our equilibrium constant for Q. So the natural log of 1.58 times 10 to the 37th. So let's do that math now. We have the natural log of 1.58 times 10 to the 37th, and we're going to multiply that by 298 and 8.314. And that gives us, if we round that, that's positive 212 kilojoules per mole. So positive 212 kilojoules per mole. I'm not worried about the exact number here because I rounded this. This is rounded as well. The point is that delta G is equal to 0 at equilibrium. We already know that. We already know delta G is equal to 0 at equilibrium. This shows you that. We have negative 212 kilojoules per mole. So about negative 212 kilojoules per mole and approximately 212 kilojoules per mole over here. At equilibrium, these will cancel out and give you delta G is equal to 0. So at equilibrium, we know that delta G is equal to 0. There is no difference in free energy between your reactants and your products. So let's think about the voltage of our cell at equilibrium. Well, if delta G is equal to 0, we plug that into here. And therefore, the cell potential, E, must be equal to 0, right? If this is equal to 0, then this is equal to 0. So the cell potential is equal to 0 volts. The voltage is 0 when our redox reaction comes to equilibrium. And so therefore, the cell dies. Your battery is dead. So hopefully this helps you understand galvanic cells in terms of thinking about changes in free energy.